This lecture is going to be on how the solar system formed. To start off, I want to ask you, why did Mickey travel to space? As in Mickey Mouse? To find Pluto. So our solar system formed from what's called a solar nebula. A nebula is a cloud of dust and gas, and a solar nebula is a cloud of dust and gas that eventually will form a solar system. The center condensed due to gravity, and pressure increased. Remember, anything that has mass has gravity, so these dust particles slowly, over a very long time, collected and pulled together. The center became hotter with the increase in pressure and denser until fusion began. Once fusion starts, that is sort of like the birth or the start of a star. The leftover nebula that did not get pulled into the sun formed the planets. 99.8% of all matter in the solar system is the sun. That's incredible. The solar system is the sun and all of the objects that orbit it. The formation of the solar system occurred around 4.5 to 5 billion years ago. Typically, I'll use the 5 billion year mark. Do you remember how old the Earth is? The Earth is 4.6 billion years old, so the Earth was forming about the same time the solar system was forming. Okay, so how do our planets form? Small bodies of matter in the solar nebula are joined together due to collisions and gravity, much like the way the sun started. A planet is a body that orbits around the sun, and there are 3 parts to the definition of a planet. First, it has to orbit a star. Second, it has to have enough mass to crush itself down into a sphere. Smaller objects like asteroids, you'll notice, typically are oblong, they're not very spherical. And last, they have to have enough mass and gravity to clear its path by pulling, meaning it has enough gravity to pull anything that's close to it into itself. Pluto did not clear its path and therefore is not considered a planet, but yet a dwarf planet. We've got 8 planets in the solar system. We have 4 inner planets, Mercury, Venus, Earth, and Mars, and we have 4 outer planets, Jupiter, Saturn, Uranus, and Neptune. You may also see the terms terrestrial, so the 4 inner planets are terrestrial. Terra means land, so terrestrial planets have land or rocky surfaces. The 4 outer planets, you may see the term gas giant or Jovian, and they're primarily mostly made up of gas. Then we have 3 dwarf planets, Ceres, Pluto, and Eris. The distance away from the sun affects the planet's composition. The closer they are to the sun, the heavier elements are going to get pulled closer to the sun because they have more density and more mass. These heavier elements, such as iron, if you notice the core, our inner and outer core is mostly made up of iron, and we are part of the inner planets. The farther away a planet is from the sun, the lighter the elements or the low density elements are going to collect, such as helium, hydrogen, water, methane, and ammonia. So this is what the outer planets are mostly made out of. So the 4 inner planets are terrestrial and rocky, and the 4 outer planets are Jovian, also known as gas giants. Why do the inner planets have heavier elements than the outer planets? Because the heavier elements are getting pulled closer to the sun by the gravity. Helium and hydrogen are abundant in the outer planets. Why don't they burn like the sun? Because they are too cold and they don't have enough gravity to crush them close enough to generate the heat to start fusion. The inner and outer planets are separated by an asteroid belt, which is essentially a failed planet. If we were to collect all of the asteroids in the asteroid belt and put them together, we would have a small planet. Beyond Neptune is the Kuiper belt, which is a disc-like shape containing many small icy bodies. Beyond the Kuiper belt is the Oort cloud, which is a spherical shape, so it's not flat like the orbital planes of the planets, but it's going to be spherical, so it's going to sort of wrap the whole solar system together, and this is where the location of many of our comets are. A comet is a ball of frozen gas, rock, and dust. And when it gets close to the sun starts to burn it, and that generates a tail. What's interesting is that the tail is always pointing away from the sun. So it looks a little odd if we were to graph it because the tail is going to change its orientation, but it is always going to point away from the sun. Ancient people observed the planets wandering across the night sky when compared to the background stars. They tend to move more in relation to the background stars. So the Greek word planet actually means wanderer. The path that the planet takes is elliptical, and this is called an orbit. Johann Kepler proved that the orbits are in fact elliptical shapes and not circular. Gravity is a pulling force that every object with a mass has its own gravity. So even a pencil would have gravity because it has a mass. Since the mass is extremely small, we really can't notice the amount of gravity a pencil has. The sun pulls the planets to keep them in an elliptical orbit, which is an oval shape. Since it is oval shaped, the planet's distance from the sun varies. We've seen these words before. Perihelion, and helion means is the point closest to the sun. Helio is a root word meaning sun. Aphelion is the point in the orbit farthest from the sun. Ap means away, and helio is sun, so the point farthest away from the sun. Orbital velocity is the speed at which a planet travels. Velocity is a speed and direction. Johannes Kepler explained that the planets move faster at the perihelion and slower at the aphelion. So it means they move faster when they're closer to the sun and slower when they're farther away. When a planet is closest to the sun, it experiences more gravitational attraction, therefore speeding up. Remember, there's two factors that affect gravity: distance and mass. So since they're closer, it's going to feel more gravitational pull. 7.3 in your book is about the Earth's moon. On July 20th, 1969, Neil Armstrong and Buzz Aldrin walked on the moon. Michael Collins orbited the moon, waiting to be able to pick up Neil and Buzz. The trip took a total of 5 days. Since then, 12 astronauts have walked on the moon, with the last mission ending in 1972. NASA is now looking at going back to the moon as a staging ground in order to get to Mars. The moon is considered a satellite because a satellite is any object that orbits another. So since the moon orbits the Earth, it's considered a satellite. The moon has a diameter of 3,400 kilometers and is much smaller than the Earth. Therefore, it has 1/6 of the gravitational field. This is why you can jump higher on the moon and you weigh less on the moon, because you have there's less gravitational pull. The moon has no liquid and an extremely thin atmosphere. Temperatures can range from negative 200 degrees Celsius to about 100 degrees Celsius. Galileo Galilei saw 3 types of features on the moon with a telescope. He saw the Maria, which means sea in Latin, because when they looked up at the moon, they saw the dark areas on the moon. They thought at one point that was oceans. However, they're just dark rock, basaltic rock, much like we see on our ocean floor. Apollo landed in the Sea of Tranquility. Now, it's not really a sea, but they called it a sea again because they originally thought it was a sea, but it's just a basaltic lava flow. Highlands are the light colored of the moon. Craters are large holes on the surface of the moon, or divots in the moon, created by meteors and meteorites hitting the surface of the moon. When the moon was first forming, there was a lot of meteors or meteoroids flying around in outer space. So the moon got struck a lot. Without very much of an atmosphere, there was nothing to protect the moon, and that's what created a lot of the craters. This created an intense amount of heat, which can then melted the rock, creating lava flows. So this is the Sea of Tranquility. All the dark areas are the Maria, the basaltic lava flows. So Apollo 11 landed in the Sea of Tranquility. This is Tycho crater. It's one of the largest, most noticeable craters. And when a meteor strikes the surface of the moon, it's going to create these blasts that sort of fan out. These are called rays. The light color area is the highlands. Our moon is not the only moon in the solar system. In 1610, Galileo discovered 4 moons of Jupiter, named after him, called the Galilean moons. 6 planets have moons: Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Space probes Voyager 1 and Voyager 2 went beyond the asteroid belt to orbit the Jovian planets and sent pictures back of about 35 moons. The inner planets have typically 0 to 2 moons because they don't have as much gravity since they're smaller. Mars has 2 moons, Phobos and Deimos. Jupiter, however, has about 63 moons. The 4 largest Galilean moons are close to Jupiter and have nearly circular orbits. The space probe named after Galileo arrived in Jupiter in 1995 to take close-up pictures and get some data. Jupiter's moons. Ganymede. This is the largest in diameter, which is about 5,000 kilometers. This is larger than our moon. Our moon's about 3,500 kilometers in diameter. Callisto is the second largest. It's dark and with an icy surface. Io is a really neat one. It's the 3rd largest moon, but it's the most volcanically active moon in the solar system with sulfuric eruptions. It's the most volcanically active body because it has sort of like a tug of war between Jupiter and its other moons, and that creates a lot of friction. So that's going to be the heat source of all of its volcanic eruptions. But the sulfuric eruptions is going to smell a lot like sulfur dioxide, which is like rotten eggs. If you've ever been to Yellowstone National Park, you're probably familiar with the rotten egg smell. And it gives the sulfuric eruptions also give it the yellowish color to Io. Europa's pretty cool. This is probably one of my favorite moons. It's the 4th largest, but it has an icy surface. But the cool thing about it is it has a liquid ocean below. So NASA's actually planning a trip to Europa to sort of drill through the surface of the ice cap to see what lies beneath it. Maybe they'll find life. Who knows? But they do have evidence that there is a heat source because this ice does crack open periodically. This is Io. Notice its yellowish color and all the volcanic eruptions. And this is Europa. These lines are the cracks in which it opens up periodically. Saturn's moons. I think there's 53 named moons, but it has more than that, so we'll say 59 moons. 5 of them are large. Titan is the largest moon. It's at about, I'll say, 5,000 kilometers, whereas the Earth's moon is around 3,500 kilometers. The Huygens probe was a probe sent out to investigate some of the moons. Uranus has 27 known moons. Titania is the largest. Neptune has about 13 known moons. I think now it's 14. Triton and Nereid are visible from Earth. Triton orbits the opposite direction of its other moons and has the coldest surface in the solar system, negative 235 degrees Celsius, and it's covered in frozen nitrogen and methane gas. Dwarf planet Pluto has 3 moons. Charon is the largest. So how did the Earth form? It formed very similar to the way all of the terrestrial planets formed. Small bodies in the solar system collided. The Earth was very hot due to several reasons. The heat produced from the collisions, increase in weight of the outer layers compressed the thin layers, and radioactive material which emit high-energy particles. Now, we don't get a lot of heat from the first 2 anymore, but we do have radioactive particles that allows Earth to continue to stay warm. There were several models of how the solar system was structured. First, Aristotle, he's a Greek philosopher, thought that our solar system was geocentric. Geo means Earth, and centric means center. So he thought the Earth was the center of the solar system. The sun and the stars revolved around the Earth. He was incorrect in his beliefs, though. Claudius Ptolemy was a Greek astronomer about 500 years after Aristotle. He also supported the geocentric model, but they had a hard time explaining why some planets actually go backwards in the sky. So they continue to move one direction, and then all of a sudden they stop and move backwards for a few days, and then they continue moving forward. So to explain this, he said that planets had two motions. One was the revolution of the planet around the sun. The second was a series of small circles like a chain. These were called epicycles, and they would explain why we sometimes see planets moving backwards within the night sky. So if we were looking at the night sky, and if we tracked or plotted the location of some of the inner planets, day 1, day 2, day 3, day 4, and then, so we have this general motion that's going this direction. But then it would stop and go this way. It would go backwards, and then it would continue forwards. So to explain this, Ptolemy said that planets have epicycles and they kind of move around like this. And Earth would be in the middle. So if we look at a planet and we're tracking it, here it would generally go this direction. Here's where it would kind of stop moving for a day or so, and then it would move backwards according to our view. It would stop again as it came back down this way, and it would move forward again. So it was said that Mars had these epicycles. Nicholas Copernicus, he was a Polish astronomer in the 1500s, he proposed a heliocentric model. Helio means sun again, and centric means center, so he proposed that the sun was the center of the model. He said that all planets revolve around the sun, not the Earth. He proposed that all planets revolve in the same direction, but just at different speeds. So these epicycles that we see, or these backwards motions, occur when a planet is passing another planet. This model was confirmed in the 1600s by Galileo Galilei with his newly invented telescope. Johann Kepler, again he's a German astronomer, he developed 3 laws that govern or explain how the planets are moving. The first law is the law of ellipses, the second law is the law of equal area, and the third law is the law of periods. Each planet orbits the sun in a path called an ellipse. Remember, an ellipse is an oval shape. The shape is determined by 2 points called a focus. One point, or one focus, is the sun. The other focus is usually somewhere between the center of the sun and the planet. Because the planet orbit in ellipses, they're not always the same distance from the sun. So we've seen these terms before. Perihelion when it's closest to the sun, and aphelion is when it's farthest from the sun. Okay, here's the sun. The center of the sun represents one focus. The green is our planet, and the blue line is your orbital path. Notice it's more of an oval shape. And the other focus is going to be somewhere between the sun and in between the planet and the sun. Notice how if we change the distance of the foci, we're going to get more elliptical shapes. So if we only have one spot, we have a perfect circle, and the eccentricity equals 0. We have a circle. The farther apart we put our points, the more oval the shape becomes, or I could say the more eccentric the oval becomes. And the scale goes from 0 to 1. 1 being the most oval, 0 being the most circular. Kepler's second law states that a planet moves the fastest when it's at the perihelion and the slowest when it's at its aphelion. In other words, the closer the planet is to the sun, the faster it's going to move. It's like if you ever rode the Whip-It ride and you come to that turn, you seem to whip and kind of go fast around the turn. Planets kind of experience the same kind of phenomenon. Here's why. The law states that equal areas means equal time. So this gray sort of triangle or cone shape, it has the exact same area as this cone shape. This one's just long and narrow, and this one is shorter and wider. But if we were to do the math, we'd find that they have the exact same area. That means the planet going from point 1 to point 2 is going to travel that distance in the same time as planet 3 to 4, or spots 3 to 4. So let's put this in terms of like driving a car. Let's say this takes 1 hour. That means this takes 1 hour. But this is a greater distance. So it's like saying 60 miles per hour versus 30 miles per hour. So this is going to be faster. Kepler's third law is going to deal with the orbital period, or how long its year is, or how long the revolution is. So a closer a planet's orbit is to the sun, the faster it moves, therefore the shorter its period, or the shorter its year. Or I could say the opposite. The farther away a planet is, the less gravitational pull it's going to feel, the slower it's going to move, the longer its period, and the longer its year. This diagram compares the different planets. Remember, AU stands for astronomical unit. 1 AU is the distance between the Earth and the Sun. So the Earth has an AU of 1. The period is the year. So the Earth takes 1 year, which is 365 days. Mercury is a quarter of that. So every time we have a season on the Earth, Mercury has a year. By the time the Earth goes around once, Mercury has had 4 years. But as we move farther away from the Sun, you'll notice that the periods are getting longer. This means that one of Neptune's year equals 165 Earth years. So the Earth has to go around the Sun 165 times in order for Neptune to go around once. Think about it. So your entire life, Neptune's only going to go around half of its revolution in your entire life.